looked at the disadvantages of composites, why use in spite of them, and in the last class we started looking at the reasons why we use them, and these are the things that we already covered. So we will get on to the next set of reasons why we use composites. So the next set of reasons, which are also very important, in some cases these might be the leading reasons why you are using them. One is the fact that typically polymer matrix composites have much larger material damping. So as you know, you would have studied in structural dynamics the concept of damping. Essentially, apart from the mass matrix and the stiffness matrix, you have a damping matrix which contributes to the equation in terms of a proportionality with respect to the velocities. So essentially the idea is to, for if there are structural vibrations, for it to die down as quickly as possible. A lot of this damping can, in many structures where vibration is a huge problem, can occur through typically you have dampers, external instruments, which could be either passive damping or active damping. But in many situations, you don't need to go to that extreme. You can survive on the basis of the materials damping itself. And there, if you look at the three categories of primary materials that we looked at, namely metals, ceramics, and polymers, polymers typically have much better material damping. In general, there could be exceptions, but for example, an extreme case would be like rubber. Essentially, you would have much larger damping, and it's used as a damping material in many applications. But here, since we are primarily focusing on polymer matrix composites, though there are metal and ceramic matrix composites, we will look into details of them later on. When we talk of polymer matrix composites, the fact that they have larger material damping comes as an advantage, that you can use it in situations where vibration is an issue, but it's not a major issue where you actually need an active damper or whatever. So, for example, in the case of a helicopter, rotor blade damping is a major thing. One of the distinguishing factors between fixed wing and rotary wing for a long period of time has been the large vibrations that transmitted all the way to the cabin in terms of the passengers and the avionics also experiencing the vibrations in much more in a helicopter compared to a fixed wing aircraft. And in such situations, you need an active damper. You cannot survive just based on the material damping of this, but it's an additional thing that you have so that the requirements of your active damper are not as stringent as it would be with, let's say, a metallic rotor blades. The second set of things is in terms of the resistance to various issues that typically arise in a structure. In this case also you can look at in terms of a resistance to vibration, but here we are looking at from the material perspective. One of the important things is corrosion, because the kind of environments that the vehicle would operate in, and certain exposed structures that they would be directly exposed to that kind of an environment, and so corrosion is something that needs to be addressed, and polymers are typically good at resisting corrosion in a general sense compared to metals. So in that sense, the polymer matrix composites are also better at corrosion resistance. Then corrosion is not just the kind of the electrical or electrochemical kind of corrosion that we talked about in a previous class, but also direct chemical corrosion that can typically occur in many situations. That is also an issue, and in both these cases, whether it is chemical corrosion or electrochemical corrosion, most polymer matrix composites are much better at handling it. The next thing is in terms of the fatigue, and to some extent this is a reason why the fatigue performance is much better in the case of composites. They are able to have the SN curves. If you typically look at, if you non-dimensionalize in particular way, the reduction in the strength with the number of cycles is not as steep as it is in the case of metals. So that is a huge advantage because most structures, as you know, in the flight vehicle are exposed to fatigue kind of loading, and therefore this becomes a very useful advantage to have shifting from metals to composites. The next thing is kind of dicey. if you take metal matrix composites, you have large fracture toughness just like in the case of metals. But when you look at typical composites which are used like the polymer matrix composites, the fracture toughness is less because essentially a brittle behavior that you have. In other words, the failure strain is very small, so the percentage elongation is not large. So the area under the stress strain curve is pretty small. But there is an advantage coming from the fact that you have a heterogeneous structure where you have the fibers coming in between the overall matrix, and therefore when the typically matrix being the weaker link in this amongst these two, the crack originates or initiates in the matrix, and then when it tries to grow, it encounters a fiber in between, and therefore it finds it a little more difficult or slower to grow the crack through that. So typically it grows it around that, which is also a larger path to take, and therefore in an overall sense you typically have the kind of crack growths. If you start with the initial set of crack density the same in both situations, a metal specimen and a corresponding polymer matrix composite specimen, you would see that the growth is kind of small. But the initiation itself or the occurrence of cracks could sometimes be more because of the fact that it is brittle. If it's loaded very stringently, it can undergo fractures. So it's not that it's completely avoided, it's just that once it is there, the growth typically happens slowly. So in that sense, the damage resistance is also something superior in a certain sense, but it's, the fact that the fracture toughness is small means that the amount of energy that it can store is very less. So there are two ways in which you look at damage. One is from an impact susceptibility point of view, which is a disadvantage, as we already saw when we listed out why composites, in spite of, at that time we saw that impact susceptibility is one of the reasons why you may not want to switch from a metal to a composite. So in that sense, yes, because there the primary driving force is your fracture toughness, and that is small for polymer matrix composites. But when you are ready to go for a particular application, especially high temperature applications which involve both thermal fatigue as well as mechanical fatigue, what we call as thermomechanical fatigue, in such situations there's a lot of tailorability that you can have with this, and already the metal is giving you sufficient fracture toughness, and then to add to that, within the metal you're now having fibers which are going to retard the crack growth. So it's a win-win kind of a situation that you have over there. So the tailorability comes from the fact that it is anisotropic, so you know which are the directions in which the predominant loads are, especially the time varying loads, and then you know that if you have fibers which are cutting across, so you can see that you would have the cracks in that particular direction, because for example if this is the primary loading direction, you would have already put fibers in this, and the fact that the load is like this means that the cracks typically originate perpendicular to it. So once that is there, you know that the fibers being perpendicular to the crack growth are going to retard it. So it just happens to be the way we design this structure. It so happens that this property is actually advantageous rather than disadvantageous. Yeah.
So when it comes to a phenomenon like fatigue, it should depend a lot on the number of microvoids or the micro cracks in the material.
Correct, correct.
The composite, should it not be more likely for it to have like more micro cracks, because there are so many interfaces between different materials coming into it. So shouldn't the fatigue properties actually be lower in
Yes, it's like a lot of things affect it. So from the point of view of what you described, yes, it would reduce it. But the fact that most of the load is being taken by the fibers, and we will see today, later in today's class, that the fibers have a much lower crack density compared to typically any other geometry. See, the same material can be either in bulk or it can be in a fiber form. And once you go into a fiber form, the manufacturing process itself changes. The way you fabricate this same material, you take bulk and the fibrous form, the manufacturing technique changes, and therefore you have lesser probability of the cracks coming up. So that is the reason why you would see. So there are many things which affect the fatigue performance, of which certain things are helpful, certain things are deleterious, but overall you would see that typically for the same kind of application, if you design the composite properly in terms of the laminate design, etc., and the choice of fiber matrix, volume fraction, etc., you will typically get an advantage in terms of the SN curves not dropping as steeply as they would for typical metal of the same kind.
Sir, is Kevlar a PMC?
Yeah. So Kevlar by itself is a fiber, but it can be used, and typically it is used in a PMC, polymer matrix composite. Yes.
So that adds to the resistance to this property of damage.
Absolutely, yeah. It's good that you brought that up, because unlike many other fibers which are typically used in aerospace like carbon or glass, which have a very low percentage elongation before failure, Kevlar is one example where, because it's a polymer kind of a fiber, it's going to have much larger percentage of elongation before it fails. So in such a situation, you do have the advantage of the energy storage, not only in the matrix, but the energy storage in the fiber also aiding to a large extent, and therefore its fatigue performance is even better. Yeah. And also along the same lines, its impact performance is also much better, because it's now having a much larger fracture toughness, so the ability to absorb the impact energy is much more compared to other polymer matrix composites. Yeah, so yeah, we already discussed this. Then the next thing is again coming from a perspective of the structure performing secondary functions. It's not just that it's load bearing, it offers certain strength and stiffness, but also the fact that you have a structure. We all saw that in the triple advantages of this particular thing being in the outer is that it's a protection from the environment as well. So the kind of changes in temperatures, the kind of electrical signals, let's say coming from lightning or from some short circuit which is happening somewhere. So the kind of transfer that takes place, so there is a possibility of you tailoring that, because the structural tailoring would be dominant. You may not have too much room for this, but wherever possible, you can also utilize this. You want a certain level of insulation capability, certain level of conductivity. You can, whether it is thermal conductivity or electrical conductivity, you can kind of tailor the composite design in order to be able to achieve that. It's not a major advantage, but it's one of the possibilities that are there. Depending upon a particular location where this might be much more critical, you can try to see if you can take advantage of this. So I think with this, we have completed the all the advantages or why use composites, the reasoning behind that. Now we'll look at some typical examples of where composites are used. You would have seen probably in your own, especially those from ISRO and or the armed forces, you would have seen more specific applications. But here I just want to give you a sample so that you get an idea of a typical aerospace or flight vehicle applications. And yeah, even before we get to where you're using them, what we are looking at is what are composites over here. So first of all, we'll define, it is not like a sacrosanct definition, but essentially what distinguishes this kind of material from the other three materials, common structural materials that we already talked about, namely your metals, ceramics, and polymers. Polymers directly may not be used because their strength and stiffness are not sufficient to handle this kind of huge loads that are typically expected, the kind of stringent requirements in an aerospace structure. But compared to them, what is the typical nature of the composite? Why is it a fourth class, so to speak? So out of the typical three classes, which are the primary classes, you now have a fourth class where you're trying to mix and match between some of these materials. It's not necessary that it should be from two different baskets. It could be from the same basket, like what you are mentioning, Kevlar, for example. An aramid fiber could be in an aramid matrix itself, or a polycarbonate fiber could be in a polycarbonate matrix. There is an example of a carbon-carbon composite also. So you both could be either the same material and or within the same class that you have. For example, you could have titanium fibers in, let's say, in an aluminum kind of a matrix, which is essentially a metal kind of a composite that you have. But the important thing is that we are used to mixtures of different materials, right from the typical metals that we commonly use, because very rarely are pure metals used by themselves. Even for jewelry, the kind of gold that we use, you typically mix it with copper for increasing its ductility and shaping it much better. So similarly for structural materials, alloys, when we've been talking about titanium, aluminum, etc., but all of them are typically alloys. We'll go into some specific examples a little later. But we are looking at mixtures in all those cases. So the very way in which you name some of them, for example, Ti6Al4V means amount of aluminum and vanadium in some percentage sense along with the titanium. So that's the typical naming convention for many of the alloys. So the idea is that, yes, we are used to mixtures, but those mixtures are at much lower length scales compared to this, which is at a larger length scale. So right now we are not defining what that length scale could be, because there's so much of variation between each one of these baskets. But typically for most practical purposes, you would have somewhere between 7 to 70 microns is the range of the fiber diameters that you would have, and that is much larger than the kind of crystal dimensions that you would have in a typical alloy kind of a structure. So what we are saying is that we have to more than one material, and these materials are chemically distinct from each other, and they remain so. There could be certain surface level reactions which take place in certain kinds of composites, but it stops after that, becoming a barrier for further reactions, and the interface is kind of held very clearly, and that's why we say it's distinct, so that you can distinguish between the fiber material and the matrix material quite easily. Many cases, even just through visible inspection, if you cut across a cross section, you'll be able to see where the fibers and matrix are, even though they are of the order of 7 to 10 microns or so, especially if they are very distinct materials in terms of their optical behavior, the kind of reflection of the light that comes through them, you would be able to see. But the fact is that the interface between them remains very distinct, and because the mixture is at a macro scale. So as I said, these are the three classes of materials that you typically have, and you choose from amongst them based on the particular requirement. So the choice of the fiber is typically based on the strength and the stiffness, more so the specific values of those. And if compression is involved, not necessarily throughout its operation or service, but at least parts of its service, if compression is involved, then the specific stability also becomes a criteria. So you choose the matrix based on that fiber choice in terms of the compatibility, the physical compatibility, the chemical compatibility, in the physical compatibility, the mechanical compatibility in terms of that interface being reasonably strong enough, because otherwise if there is a fiber matrix debonding, it can lead to other types of failure, especially matrix cracking to start with, and then the overall failure of the composite itself. So you want to ensure that the choice of the two is made appropriately. But as I said, it could be across these or within each one of these brackets as well. So the most important thing is to re-emphasize the fact that these are distinct constituents, is that in terms of the interface, we are clearly seeing there's a distinction between these two. You can clearly earmark where the boundaries are, where the fiber ends and where the matrix begins. Some cases, instead of letting the fiber and matrix react and form an interface is already imposed on them in the form of a coating. So typically, for example, if you have a titanium matrix, which means it's a titanium alloy, and you want to put a silicon carbide fiber in it, you typically would coat it with pure titanium. If you just put directly the silicon carbide in many of the structural alloys of titanium, the interface might look reasonable to start with, but with even a slight bit of loading, especially fatigue kind of loading, that interface can give up very easily. But if you coat that silicon carbide with pure titanium, that coating also sticks well, and then when you put this into the titanium alloy, then that second interface that is developed is also pretty strong, and it works out pretty good. So it's also the reason why fibers like boron, etc., are not used as it is. A boron fiber is typically a boron core with a carbon coating that you have, and that is also very useful. One is for the chemical compatibility, the other is also in terms of the mechanical compatibility. Sometimes you want to introduce a certain level of surface roughness so that the bonding is much more stronger. Okay, so the way you introduce those surface roughnesses is not by introducing cracks, but by the way the fiber is made. You try to grow something over it. One typical example that is in the research mode a lot these days is in terms of growing carbon nanotubes over the carbon fiber, so that these, when grown in a transverse direction, it could be in any direction in the transverse plane, but essentially these are coming out. So essentially you can think of it as a very rough surface carbon fiber where the interfacial strength between the matrix and the carbon fiber is much more. So something like that. But there's a lot of issues involved in doing that, which is why it is not on the large scale yet, but it's just a matter of time, as it has happened with many other technologies also, that they would eventually find the light of the day. Yes?
Why the titanium coating is sticking very well to the thread but not the material?
Yeah, very good question. So it's the kind of the alloys that are there in the alloy, the other elements. For example, you have aluminum and vanadium. The crystalline structure that forms is such that it's much smoother. So you typically would have the interface from a mechanical bonding point of view is not that good. But once you put the pure titanium on it, pure titanium sticks obviously much better to the titanium alloy. On the other hand, it also sticks much better to the fiber, silicon carbide fiber in particular, because of the kind of the structure, that the microstructure that silicon carbide has in the fibrous form, and the kind of structure that the titanium has in its pure form, are much more compatible compared to the titanium alloy. So it's the question of the difference between the crystalline structure of pure titanium on the one hand and the titanium alloy on the other hand, how it typically happens, and that change in the crystalline structure could change in terms of the compatibility and the mechanical interfacial strengths.
So when it comes to the metal matrix kind of composite, how are the fibers laid down, and then because I mean for a metal the heat treatment and all would be very critical. So then it cannot be done like how we do it in a polymer where we just have it
Yeah, yeah,
and then
yeah,
we
yeah,
bake.
yeah.
So how is this done in a metal?
Yeah, so it's quite a challenging thing compared to polymer matrix composites, metal matrix composites, and there's a lot of proprietary thing. For example, titanium matrix, very few people are aware because this is held very confidential. But we can take the example of aluminum matrix, which is quite commonly used, and also even many academic labs also typically do that. So there, yes, heat treatment and other things you'll have to look into from a point of view of an aerospace application, but typically how the people make these specimens, you typically make the aluminum alloy and you let it kind of get back to the room temperature, so it kind of solidifies. The that kind of a crude approach typically will reduce the properties of your aluminum fiber to a large extent, also the heat to which that fiber goes. But typically you would use in such metal matrix composite fibers which are capable of handling higher temperatures. So even in a molten metal, they would be able to retain their structural properties to a large extent through the process. So it's very different from metal to metal, and also depends on the kind of fiber you want to put within them. but this is typically the way it is done. You will not get it in the form of the pre-pregs, for example, that we were talking about, or even the SMCs and BMCs, the sheet metal compounds or bulk metal compounds that we are talking about. But there's also a lot of interest in additive manufacturing of this, 3D printing as it is called more colloquially. So where people are looking at using these in a powdered form, and then you are essentially bringing it based on a certain program that you have, you're trying to bring it out and you try to place the fibers as the powdered matrix in a molten form is being laid out. So there things are much better in terms of the ability to bring in certain orientations and the arrangements, etc., in a much more close way to what you have designed it. But the properties of such materials, to a large extent, it's improving. But if you compare the same composite being made out of 3D printing and out of the conventional subtractive kind of manufacturing, you would see that the ones with the subtractive manufacturing have superior properties. But the gap is kind of closing with the technologies of the additive manufacturing increasing over a period of time. Yeah, so, yeah. So, the fact that the interfaces are different doesn't necessarily always mean we are talking of a fiber reinforced composite. You could have particle reinforced composites also, what are known as particulate composites. And there also, this definition typically holds that you have a distinct interface between those particles and the matrix that is encompassing them. But nonetheless, in aerospace or flight vehicles at least, you find that the most popular composite that is used is the fiber reinforced rather than the particulate reinforced. You find a lot of particulate composites being used, for example, in the automobile industry, especially in passenger cars which are commercial, which general public can buy. But once you go to even there, the more high-end racing cars, etc., you typically would see more of fiber reinforced composites compared to particulate composites. So the question is why this particular geometry? We already seen certain superior properties of fibers, etc. But the whole idea when you're going for a mixture is to take advantage of all the components of that mixture in some sense, and you're arrive at some kind of an average property which is better than each one of those two individuals operating separately, two or more individuals operating separately. But in that mixture, it's not only the choice of the two materials, but also the choice of the geometry of that reinforcement material, what kind of a geometry you typically choose. So even in civilian structures, for example, when you choose the steel reinforcements, what are called as rebars, the kind of choice that you make of the steel that you have, one is in terms of the material, but also in terms of the cross-sectional geometry, the way the surface finish is made, etc. That also plays a role in terms of how the overall reinforced concrete is going to behave. So we will first look into why this particular geometry is of significance in flight vehicles which are much more demanding, or any other more demanding kind of structures. So to do that, we will first look at certain typical fiber materials and look at what kind of properties they have. What is the comparison of those properties with their typical bulk kind of materials, and therefore we will see the superiority of the property of the same material in a fiber form as opposed to any other form, and then we will take it forward. So some of the carbon fibers that are typically used in flight vehicles today, be it for the fixed wing or rotary wing, or even the rocket kind of applications or missile kind of applications, or satellites even, you typically have a lot of them made out of carbon fiber composites. And carbon fiber composites, you typically have two extreme situations. One case where you have the Young's modulus, some class of carbon composites, the fibers. We are still talking of just fiber materials. We're not talking of the composite here. So this is one of the components of the composite. So when you talk of a particular fiber, there are different companies which make it, where Toray is one example, Hercules is another example. There are many, not too many, in fact about 3 or 4, most of them based in the US, Japan and France. Some of these which make these fibers. Of late, CSIR lab NAL in Bangalore has developed certain carbon fibers, and it's outsourced that technology to some of the private industry to manufacture them. But most of them are manufacturing these fibers for other applications than flight vehicles. The flight vehicle application, the stringent requirements, we still have some way to go in producing large quantities that are required for many of these applications. But there is a movement towards that. Now, within each one of those companies, when you say carbon fiber, there's not a single particular carbon fiber. There are a lot of variations in that. One is in terms of the availability of that material, in terms of either unidirectional fibers or in terms of the weave patterns, etc. But within that individual fiber itself, there's a lot of variation in the property. So what we are looking at right now is not the form in which it is presented, which it can have a lot of variations, but the very individual single fiber, how the properties can vary for the same material, carbon composite, the carbon fiber that we are talking about, from the same company, Toray, for example. We take 2 examples over here. You see that the Young's modulus for one of them is very large compared to this, so 324 GPa and 588 GPa. On the other hand, the other thing is getting reversed, that your ultimate tensile strength is only 3.82 gigapascals over here, whereas here it is 7 gigapascals in terms of how they are typically made. So the again, this is again a very, very proprietary, confidential way in which these fibers are made. So, but people are aware, at least in terms of what is the starting material, raw material from which these fibers are made. For example, we are focusing right now on carbon fibers. So you typically have what is known as a precursor. So this precursor material could be either pitch-based carbon, or it could be pan-based. What is pan is a short form for polyacrylonitrile. So it could be, or it could be rayon, or it could be a few others. These are the 3 very common forms from which the fiber is made. So one is what you start with, and the second is the process through which you arrive at the fiber. That makes a huge distinction in terms of this, because the starting point to a large extent determines in the eventual fiber what is the percentage of carbon that you would have. So the purer forms of carbon, as I mentioned in a previous class, are typically called as graphite fibers. But within that also, in terms of the not only the additive elements, but also the kind of surface finish that you have, etc., all of that makes a huge difference in terms of their properties. So there's when you say carbon fiber, it's not a single kind of animal that you're talking about. There's a whole species out there, and you have to look at what is your specific requirement, depending upon whether it is a high stiffness kind of a requirement, in which the M60J might be more conducive. If it's a high strength kind of a design, your T1100S or T1100G, 2 different fibers, but similar kind of properties that they have, would be much more suitable. And you see that there is some difference in the density also, because we are taking up 2 extreme cases, but most carbon fibers will typically have a relative density of 1.8. So this is very typical. This is more of an extreme case. We are trying to go for a very high modulus fiber, and therefore the density that it is having is slightly higher compared to the typical carbon fibers. Yes.
Testing methodology, how it will it is distinct from the metals?
Yes, obviously, because see, the support matters a lot, because these are things which can, tension to some extent is something which is handleable, but in terms of how you're going to grip that, there's a lot of thing. But again, there are standardized tests that are there for these as well. So you go ahead and do that. But in terms of actually doing it, it's much more involved, and you can't do it in just with a typical kind of way in which you make the specimens for a UTM to measure the same properties for a metal or something like that. But the more critical thing is in trying to get their other properties rather than the tensile in terms of let's say the compressive properties in this direction. Itself is a challenge. Now the compressive properties in this direction, you need to provide the appropriate supports, and you need a modeling basis to understand how the support is only to avoid it from bending. It's essentially like buckling. So it's essentially a geometric failure. You want to avoid that, and purely you want to get to that. So what kind of supports are there? So again, all of these are kind of standardized to some extent, and there are ways in which you typically achieve that.
Is there a limit on the size of the fiber?
Yes, there is. There is. We will look into that in a small exercise that we will do shortly today itself.
Sir, I have the same question. I mean, for a metal, we usually have a thin area like a barbell, I mean, a dumbbell shape or
Correct.
something like
Correct.
that,
Correct.
so that it doesn't fail when we are molding.
Mhm.
So, fiber testing also, does that apply or?
Yeah, it does. See, just that you will not get that fiber itself thickening out. You would see the way the fiber is typically attached. You would have some kind of a composite which is there. It goes into a certain matrix, and that matrix is what goes into the grip rather than the fiber itself, because once the fiber goes into it, there is possibility of surface damage that occurs, and that will become the place where the damage occurs. It's good that you brought about this dumbbell shape or a dog bone. The reason why we do that is you want to avoid the Saint Venant's effect. So the end effects that are typically there, you will typically see if you take a specimen which is of constant cross section, a prismatic cross specimen like this, and you put this directly in the grip and test it, almost always you will get the failure occurring where the grip is there, because the boundary condition becomes an issue, which is why you try to make it a bigger cross section over there, and then you're essentially testing the strains over here to make sure that stress strain at this location is what you're trying to compare, and therefore what comes out of that, the Young's modulus and the strengths, etc. So the same concept, you just can't have a fiber manufactured very easily which kind of is lower thickness here and increases in thickness there. Still there are issues in terms of the grips and things like that with a larger diameter fiber, so you still will have issues. So you typically put it into a matrix and cure that, and then you typically apply that. So again, as I said, is the least of our problems, the tensile tests. It's the other tests that are much more challenging, and many people who can get tensile properties very easily in a characterization will not be able to do that. You need to go to some specialized entities to be able to get properties. To a large extent, the manufacturers, if your specific applications towards that, they will give you from their own tests what those properties are, so to you have a certain thing, but you cannot always be sure of that. So the kind of factors of safety and other things that are involved with that are much more that you need to go do, because there's a lot of variation in properties, and or you have to go for a probabilistic or non-deterministic kind of modeling. Yeah, so each of them have their own notation in terms of how they arrive at particular numbering, etc. So we'll not go into that. It's more of a, if you just look at, go to any of these company websites, you will have those brochures where they will list all these materials that they have. I just took two extreme cases, one with probably the largest at that point when I sourced this. This was the largest stiffness carbon fiber that Toray was making, and this is the largest strength in terms of the ultimate tensile strength in the longitudinal direction that the same company was making with carbon fibers. Oh, that's the elongation. Yeah, glad you brought that up. Yeah, I should have put it in a separate line, probably didn't have space. So the failure occurs at this level of elongation. And it's a good point that you brought out. See, when you're going for a larger strength, you're also able to increase this. So One of the reasons why you might be using this over that in certain application is not necessarily its large strength, but also the fact that it gives you larger elongation and maybe certain impact application. The fracture toughness of this material might be composite made out of this fiber might be better compared to that. So that's another thing. Yeah. Yeah, I think I covered that. Yeah, so this is more conventional. So this is the kind of fibers which are commercially available. I don't know if they will provide it to everybody. There are also sanctions in terms of which countries can source it, and within the country what kind of a user can source it, and so on and so forth. Certain things which, for example, academic institutions can buy, DRDO lab may not be able to buy in India. So there are certain restrictions over that. And this is more from a historic sense. This is from a table from your textbook itself. Textbook being 2006 editions is much more older information that you have. But it compares not only carbon fibers like what we did over there, but also along with this, these three carbon fibers, it's also looking at glass fibers, two kinds, silicon carbide fiber, boron fiber, and two Kevlar fibers that you have over here. So just to bring in the distinction, just like in carbon itself, you can have so much of a variation. Similarly, in glass also, you can have quite a bit of variation. Two very commonly used glasses, one for structural applications and therefore called S-glass, and one mainly for electrical applications, for insulation, etc. You call it E-glass. Electrical applications could also involve electromagnetic applications, so in terms of the insulation that is involved. So typically in an aircraft, a lot of these communication equipment with the air traffic controller, etc., are housed closer to the nose. And so typically you do not want to use carbon fiber composites close to the nose. You would use a glass fiber composite. And if the structural requirements are not very stringent over there, though sometimes impact could be an issue. But typically you would see in some situations E-glass being used over there. But it's more than these primary structures, it's more in terms of the interior. You have secondary structures, certain compartments for certain things where electrical properties become more significant. You would typically use the E-glass material. So you see that the densities do not have too much of a difference within any category. Here we saw a little bit more because I was taking two extreme conditions. But here if you look at all the carbon fibers, they all have about 1.8, whereas this is about 2.5. Relative density is what we are talking about, which means that this will be, the density will be in SI units will be 2,500 or 2,540 kilograms per meter cube. So you would not find too much of a variation, but you would find, and usually typically in many situations you will not find too much of a variation in the stiffness also, or the variation will not be as high as in the case of the strengths that you have. So the strengths, for example, here it is 2.5 GPa and 3.5 GPa. So it's very clear why you would prefer the S-glass for the structures. In fact, its name itself is because of that. Then coming to silicon carbide, which we've been talking about quite a bit, it's essentially ceramic. So if you look at all of these that except for the last two, they're all ceramic kind of fibers. So glass is also a ceramic. It's more of an amorphous kind of a ceramic. And many of these carbon fibers are essentially crystalline in nature, depending upon the levels of purity and the way the fiber is manufactured, and which is what gives them much more strength over the bulk carbon that you have. And Kevlar, again, it's a polymer chain. So how that polymer chain is essentially getting extended in the fiber form and getting oriented in a particular preferred direction, instead of typically how the polymers would be all over the place in terms of their direction of each one of those monomers being a part of the polymer, orienting in different directions. So that is kind of brought to much more order when you get into the fiber kind of. And again, so just like we were distinguishing between carbon fibers here, between E-glass and S-glass here, you can look at the two classes of Kevlar which are listed here. There are many more which DuPont makes. So essentially it is a chemical name, it's aramid, but because DuPont makes it, they give it a trademark name, which is what is Kevlar. They make many other Kevlars as well, but these are the two more commonly used Kevlars. The Kevlar 49 is superior, and it's what is used for a lot of aerospace structural applications. Kevlar 29 has inferior properties. In fact, you can see a huge difference even in the Young's moduli, which typically doesn't differ too much. And here the strengths are pretty much the same. The reason for the different kind of nomenclature there is primarily because of the difference in the Young's modulus. But once again, as you see, the density hardly changes, maybe in the third place or so it might, but essentially it's the same for the two types of aramid fibers that you have. Now, in terms of the specific choice, there could be other things than the specific strength, specific stiffness, and the specific stability. One example that we already talked about is in terms of the electrical functionality that you might need to have in addition to, so for the nose cone, you might, because there is both the possibility of the impact as well as the requirement of the electromagnetic kind of shielding happening because of the kind of carbon fibers that could do. So you typically would have S-glass rather than E-glass because you need a certain level of strength and stiffness as well. So there are many things that go into a decision making in terms of this from a purely technical point of view also. We already talked about many a times the non-technical aspects. I'll not go into that. But purely from the technical point of view, there are things other than those three specific properties that we talked about, which can also govern the particular choice of the fibers. So within these, you typically classify fibers themselves as what are known as basic fibers and advanced fibers. The basic fiber, and this is primarily done on the basis of the modulus, but also turns out to have a correlation with the cost as well. So basic fibers are typically inexpensive, relatively speaking at least, and the advanced fibers are much more expensive. And the ballpark line in which this is divided, again, is not a very, very rigid number, so to speak, but just to have an understanding, anything which is less than 100 GPa is typically, in terms of the Young's modulus, is typically, for example, in these two cases, or the Kevlar 29, those would all have a Young's modulus less than 100, they would be classified as basic. So these are typically used where the cost plays a very critical role in the choice, quite obviously, and also where it's used in much larger volumes. So if the cost is highly different, but still it's used in very small volumes, you might still go for the superior performing fiber. But especially when it's high volume, then the difference has a multiplying factor, scale-up factor, and therefore you would typically use a basic fiber. And E-glass, S-glass, and also Kevlar 29, as we saw, are classic examples of this. And one such application is in automotives. There are a number of cars which are made, or even of a particular model of a particular company is much more typically compared to the number of aircraft, let's say an Airbus A380 or a Boeing 787 is made. So you typically would have, though each aircraft might have large usage, overall in terms of a certain life cycle that you have, not life cycle of the product, but in terms of the manufacturing units life cycle, how much of this material you're going to use will typically be much more in the case of the automotive, and therefore there you go for a lower modulus you are willing to go because of the cost advantage that you have. Then the other is of course where this falls, and also all these middle quantities fall, right from the silicon carbide all the way to the Kevlar 49. That kind of a list is what we call as the advanced fibers. They have moduli typically greater than 100 gigapascals, and because of the manufacturing processes involved, the raw materials involved, etc., combination of those two rather, you would typically have these available at much higher prices, and examples are your Kevlar 49 and the carbon, whether it is high moduli kind or the high strength kind, both of them are quite expensive. The exotic applications include not only aerospace, but also a lot of sporting applications. In fact, some of the initial applications in the early 1970s started off with tennis rackets, golf clubs, and bicycles, etc. And even now, that kind of trend kind of continues. Some of these could be those which are rejected for aerospace applications, but still of fairly good properties and might be used over here for some of these exotic applications. But again, the costs are much larger compared to the basic fibers. Then, of course, the reason why you're going for a costly fiber is that the performance increase that is there will justify the cost increase. So, in terms of how much the performance increases, be it the range or be it the let's say this maximum speeds that the aircraft can go to, or the payload carrying capability in terms of a percentage of the overall aircraft weight, etc., you would see quite a distinct change, and that extra cost that you're investing in the material and in its fabrication, etc., will be recovered over the life cycle of that product in terms of using it because of lower fuel consumption, for example, or your ability to travel faster and therefore charge for the tickets, you could charge more. So in terms of the end operator, how it's going to become more economic sense, that is what dictates. So you have to think of it from a much larger perspective in terms of the end user and their overall usage of that particular product over a long period of time. And also in this comes in the maintenance aspects and how frequently you have to replace a particular component. So what is the cost involved with that? All of this will come into it, and typically the negotiations, if you see, between the aircraft manufacturer and the airline, you would see a lot of these things being discussed threadbare and also with appropriate proofs and things like that. So all of this comes into picture in the decision-making process for the designer also, keeping that in mind, because you make something really exotic, you spend a lot of money, eventually there are no buyers for it. You have to make a use case and say how they will benefit in the long run, even though their initial costing might be high. So here we have a plot of the Young's moduli versus the tensile strength. We are not taking into account the density over here. So these are absolute values. In the aerospace case, it would be much more important to divide both of these by the density and or take square root, etc., as we have seen before. And for the case of the compressive applications, by the density cube. So even in terms of if you look at from an absolute point of view, the kind of material that you have, and it's pretty much this tries to take care of all the structural materials, and you see that there are certain baskets that you can see where these are. This is this particular thing, the source is ANSYS. So ANSYS has an educational package where you can extract this information either for all the materials that they have or certain classes of materials, or you can put certain constraints in terms of certain things being within certain ranges, and then essentially out of that you can arrive at some of these quite informative plots, I would say. And there's a tendency to move in a certain band, in a diagonal band from the origin. So in other words, which is actually quite an advantage for the designer, because you're not suffering too much from in terms of if you're choosing a totally different class of materials which has a higher Young's modulus, you might not lose out on the strength. But within that, you would see there is a contradiction. Like what we saw in the previous slide, we saw those two carbon fibers. One case you wanted higher stiffness, but you ended up with a lower strength. So when you're going to such extreme cases in terms of the best performing materials, etc., you will have when one increases, the other decreases. But in terms of an overall class of materials, for example, these are all green, are all foams that you're talking about. These are all glasses that you're talking about in the pink background. There's certain non-technical ceramics. So you see the civilian application over here, the concrete over there. And similarly, you see this particular thing is the polymers that you have over here. And then the ones which have been conventionally used for a long period of time, you see the metals and alloys over here. So there is quite a spread, but this just gives you an idea of what kind of materials typically stand. And as always, in most situations, you'll see the strengths are in megapascals and the Young's moduli are in gigapascals, because your typical failure strains are of the order of percentage or 10% at the most for many of these structural materials. So you would have an order of magnitude difference in the strengths and the moduli. And this is a log-log plot, as you can see. So you see typically it's varying in 10 powers of 10, both in the numerator, in the y-axis as well as the x-axis. And just like we were talking about, there are certain quantities like what we are talking about for the stability. It is essentially E by rho cube, etc. There are certain other things which are derived based on certain other considerations for certain specific applications, where you will have certain powers of the tensile strength divided by the Young's modulus, etc. So these typically help in the decision-making process as well. So the actual features which are involved with these are slightly more complicated beyond the scope of this class, so I'll not look into that. Those of you who are interested in this, there are many labs in our department as well as the institute which have licensed versions of ANSYS. So you can look at the ANSYS and see what are the typical theories behind each one of these and why each one of those lines are important. So many of these will kind of give you a guideline in terms of what is the range of materials that you can choose from, and within that range then you perform an optimization instead of looking at the whole class. So these typically help you with shortlisting the candidates before you go ahead with the actual design. Yeah.
The components are looking like subset of metals and alloys. Like is it looking like we are not gaining anything over metals or?
Again, see, these are absolute values because we are plotting. So the main reason why you're going for them is the lower density that they have. So once you bring the density into it, it will go up. So it's actually good that composites are actually doing so well. Even in an absolute sense, you're seeing that it's kind of pushing the limits. But once you bring in the density in the denominator, you will see that it goes much better. Okay, next we look at specific questions we were asking even in today's class earlier. We mentioned that there are two different kinds of reinforcements that are typically used, particulate and the fiber. And why is that fiber so very important? To some extent, we got the answer for that in terms of the properties we saw in the previous slides. The properties are much superior compared to the corresponding bulk materials that are there. So we would like to see the actual reason why this is the case, that fibers perform so well compared to their bulk materials. So in this sense, it's important for us to understand what are material properties. When you say a particular quantity is a material property, for example, we know the mass density in kilogram per meter cube is a material property. But similarly, you say ultimate tensile strength, for example, is a material property. Young's modulus is a material property. Fracture toughness is a material property. When you say something is a material property, obviously from the very name, it's very clear that it depends only on the material that you're using. It should not depend upon the geometry that is involved. But you already mentioned, for example, the dog bone kind of a thing. So the ASTM standards or any other standards would typically tell you exactly what is the particular size and shape that you want your specimen in to get the right kind of results. So obviously, even though we are calling it a material property, there is some influence of the geometry of the specimens that are being tested in terms of arriving at those properties. Now, we are trying to push that to a certain extreme when you're going to what are called as fibers. So fibers, as I already mentioned, typical fiber diameters of the order of 7 microns to about let's say 70 microns. Most of them are in the 7 to 20 micron range. It's only when you go to boron or silicon carbide, a few other fibers which will be a little more than that. But these are fairly small diameters that you're actually looking at. And you go to the other extreme where you're looking at what are today being touted as the future materials, be it graphene or carbon nanotubes, etc. Even lower dimensions you're going into. The fact that they are called as nanofibers is that their diameters of the order of certain in nanometers rather than microns that we are dealing with in typical carbon or any other fibers that we are using today. So we are essentially trying to push that limit in terms of the size of the fiber. So if you're looking at the same cross section, it's essentially a cylinder. A fiber is a cylinder with a circular cross section to the extent possible. There are certain reasons why sometimes you might go for non-circular cross sections also, let's say elliptic cross section, etc. Very exotic, rare applications. But it might so happen that the manufacturing process sometimes, if there's not much control, you could have slight deviations from the circular cross section, and therefore many non-deterministic techniques will take into account the variation in the shaping as well, apart from size of the, which is the diameter of the fibers. Now, the fact that we are calling it a material property, obviously there should be some link to the material in spite of that dependence on the geometry which is dictated by the standards saying that this is the kind of specimen that you have to test. What if I just for the sake of it go ahead and test a specimen which is, let's say, double the cross-sectional area, both in the center portion of the dog bone as well as the end portions. Let's say increase in one direction the lengths much more. Will I get very different properties? Let's say, let's not even go to composites now. Let's take a metal, for example. Let's say I have an aluminum specimen, one I have designed exactly according to the ASTM standards and I am testing that. Another case, one particular cross-sectional dimension, I double it. Not just at the ends or at the center, but both. So essentially it's still a dog bone, but it's having overall dimension much larger. So will the end result that I want to get is the stress strain curve in the tensile test that I'm doing in a UTM, universal testing machine. You're putting the strain gauges, you get plotting the readings of that strain gauge versus the stress that you're applying, which could be, let's say, the true stress, or it could be the whatever stress. But essentially, for between the both specimens, you're looking at the same quantities that you're plotting for both. So now from that, you essentially for the in the initial stages of stress strain, you get the slope of that almost straight line. You get the Young's modulus where it goes to maximum and then tapers off. You get the yield strength, and then eventually you're at the failure you get your ultimate tensile strength, or UTS sigma U as we've been calling. So will these two results be very different from each other? Exactly, right. So to some extent, the fact that they are defining certain standards means that there is an influence of geometry, but it may not be too much. So what you're saying is also right, what they're saying is also right. So essentially the scatter will not be so much, just that you don't want somebody claiming by testing a different kind of a specimen much better properties for whatever material they are manufacturing compared to somebody else, some other manufacturer making the same material. So you want some level of standardization going forward, but essentially it should not make too much of a difference. Now, it's good that you mentioned scale, because here we are talking about all of them being in the order of, let's say, a few centimeters or a few millimeters in terms of the specimen size. But now what we are going to talk about when we go to fibers is the microns that we are going to. And eventually, for example, you're looking at carbon nanotubes, etc. You're looking at nanometers that you're essentially going there. So there is something that is happening in the physicality of the material which is undergoing a change when you are going for lower and lower dimensions, which is why the fiber becomes so attractive. Because at the end of the day, it's the same thing. I start with a specimen which is more like a rod, and then I'm ending up with a fiber which has very inferior properties in the transverse direction, shear, etc., but which we want to eventually make up with the matrix. But right now we are leaving out the matrix, focusing only on the fiber material. We are saying, well, glass doesn't perform very well if it's taken in bulk, but a glass fiber does so well. Carbon in bulk may not perform so well unless it's a diamond or whatever. So, but you're at the other end of the spectrum, a carbon fiber and a carbon nanotube or graphene performs so well in terms of its strength, stiffness, etc. Even when you divide by the density, you get very, very superior properties compared to the same material in bulk. So there is something that is happening in transition from going from the bulk material to the fiber kind of a geometry. So even though we are calling it a material property, there is some influence of the geometry which is coming into it, and we have to see what that geometry influence is. And it could vary from material to material. In the previous slide, we looked at different kinds of fibers. Some are ceramic fibers, how they behave. Some could be metallic fibers, some could be the aramid is a polymer fiber, the Kevlar that we talked about. In each one of those cases, there is some physics that is happening at the material level, material science level, much smaller dimensions, that is essentially increasing the property values as we reduce the dimensions. See, the individual load carrying capacity has to reduce when you are actually applying a load. For example, I'm taking this, and I apply certain number of newtons of force on either end. I'm trying to pull it, it will fail at a particular point. But now if I cut it into half and try to pull it, obviously the load at which it will fail is much lesser, right? So I'm not talking of the load that is involved. The load will depend upon obviously the geometry. Now what we're talking of the stress at which it will fail. What is the stress at which it will fail is what helps us to get to the material property, what we call as the ultimate tensile strength, or as a slope of that stress strain curve, the Young's modulus, whatever. So that should typically not change. That is what, or even if it changes, it should not change by too much is what we are looking at. But here the two examples that we had are both macro scale dimension specimens. So this is also the order of, let's say, a centimeter or so, and that is about half a centimeter or so. So you are essentially dealing with still at a macro dimension where the overall behavior of the material might not have changed. And also the way I went from one to the other probably is just to cut a specimen like this. So the manufacturing process for the two might have been the same except for that cut that is involved. So in terms of the micro structure of these, there might not have been a change. But when we go to fibers, it's not going to be made by kind of cutting these. It's the fiber itself is going to be manufactured with that particular dimension using a different technique. So that is going to obviously change the microstructure in a particular way that your strength and or stiffness and many other properties could become much more superior to what they were with the bulk material. So let's take the example of material, what we call typically as a material property, which is of interest to us as a structural engineer, is the ultimate tensile strength. So this is in gigapascals, and when you're talking of a fiber, you also need to mention, because it's slowly getting into the anisotropic regime, you have to mention not only that it is tension, but tension in which direction. So there's a transverse tensile strength, and there is a longitudinal tensile strength. So what we are talking about here is a longitudinal tensile strength. Now the question is this a material property or a geometric property? Both, yeah? Exactly, exactly. So even though colloquially or even in many professional circles we call this a material property, you can't say that it is glass, so it will have this ultimate tensile strength, right? So it also depends on the form factor that is involved, and yes, at the same orders of magnitude of the form factor, you may not find too much of a difference. But once you go for orders of magnitude difference, let's say from let's say centimeters to the level of microns and then eventually to nanometers, yes, for the same material, because of the way you prepare that specimen or fabricate that specimen, there is going to be a change. So there is a level of geometry playing a role over here also, but just that geometry is playing a role only because the manufacturing process is different. So essentially you're changing the very character of that material through the manufacturing process in terms of, let's say, if it's a Kevlar kind of a thing, you're essentially making sure that the monomers in the polymer are all getting oriented in a more closer to a particular direction, which is parallel to the eventual fiber direction that you're getting. If it's certain crystalline material, like say a metal fiber that you're making, those crystals are all getting oriented in a particular way through the way in which you're manufacturing that material over there. Same thing with the case of carbon or with glass as well. See, carbon and glass are both ceramics, but in one case, carbon is typically crystalline and glass is amorphous. But the way you make the glass is through melting it and getting it out. Slowly, it loses its level of amorphous nature, and then there is a certain orientation that is taking place over there as well. So, essentially, a certain ordering is introduced into the more nuanced or better manufacturing process that you're employing to get these smaller cross-sectional dimensions, which is what we call as fibers at one end of the spectrum, as opposed to rods at the other end of the spectrum. Now, these are things that I've already discussed with you, but I typically go through this in many steps so that I get the interaction from the audience, the students, and then try to arrive at a thing. But many of these, since I've already talked to you about, I will just read through it. So, do the material properties depend only on the chosen material or on the shape and size of the object? You already answered that there is a certain dependence on shape and size if we are going for an order of magnitude difference in that shape or size. But as long as it's in the same order of magnitude, it should give a small change, but it's more of a scatter because of various reasons. It need not be a major change that is happening over there. Next is, should the ultimate tensile strength depend on the fiber diameter? And yes, so as you're nodding, so yes, it does depend on the fiber diameter microns, as we have discussed so far, because the smaller the fiber diameter you're essentially moving towards, you're essentially making that orientation much better. But in addition to that, there's another other thing that we are doing is that even if we don't, at a certain level from one fiber dimension to another, if you're not making too much of a change in the ordering, in terms of the surface finish, also you're going to get a much better surface finish, which is much smoother in the sense that the cracks that you're going to have are much lesser. So in other words, we talk of what is a quantity called crack density, which is essentially the crack area multiplied or sum of all the crack areas of all the cracks that are there on the surface divided by the unit area of that surface of that fiber. So let's say it's a fiber of length L and radius R. So 2 pi RL is the outer surface area. In that 2 pi RL, what is the area of the cracks that you have? So there will be multiple cracks, and you are essentially summing up the areas of all those cracks, dividing by the 2 pi RL. So we call that as a surface density of the cracks. This crack surface density is going to reduce as you're going to go into smaller and smaller dimensions of the fiber. In other words, the cross section is becoming thinner and thinner, because essentially in the limiting case, you're moving towards what we already called as whiskers in the previous class. That is more from a current technical point of view, what is the minimum you go to. But from a theoretical point of view, from a material scientist point of view, what is the smallest dimension that you can go to for the diameter of the fiber? Yes, that's the order of it, but what we are essentially moving towards from a chemistry point of view. What is the chemistry involved as you're going to smaller and smaller dimensions? So can you go perpetually towards zero? No, obviously, right? There is a certain limiting case that is involved from the very chemistry of those materials. What is that? Exactly. So if it is a structure which involves a material which involves molecules, it's essentially the molecular dimension. If it's a structure which is a single element, it's the atomic level that we are essentially pushing towards. We may not get there in terms of the actual feasibility, in terms of the manufacturing technologies that we have, etc. But from a theoretical point of view, from a material science point of view, that is the limit towards which we are pushing this whole thing. And typically, that will be essentially whatever strength, because we are now talking about the tensile strength, we are essentially talking in the molecule case, some molecular strength that is involved between, let's say, covalent bond strength or whatever. And similarly, in the case of a material which is a single element like carbon, for example, it's essentially, there is the atomic structure that it is having. So two carbon atoms are coming next to each other. There is a covalent bond which is being formed between them. So you're essentially talking of the atomic sizes that are involved. So that is, even in whiskers, you don't go to that level, but from the technological point of view, what is the current state of the art? What is the minimum that I can end up with? And there itself, we know that the, as I discussed, the disadvantages of using whiskers in the previous class, we are talking of short fibers there. You don't get very long whiskers. So that is an issue. And with those short fibers, then putting it into a matrix and orienting it in a particular way becomes much, much more challenging, and therefore the properties are going to be not as promising as the whisker itself, individual whiskers property was. The composite may not be reproducing it, mainly because of the random nature in which these orientations might go in the eventual composite. So let's track back. We're still not getting into composites. We're talking only about the fibers over here. So to take that into in a more engineering sense, we are looking at a plot between the ultimate tensile strength in the longitudinal direction of the fiber alone, no matrix there, so it's not a composite, and we want to plot it versus the diameter of the fiber in microns. Of course, when this microns becomes millimeters or centimeters, it becomes essentially a rod. So you know that for such a situation, the bulk properties of that material will come into picture. So it's, if I make this plot, it's going to essentially move towards being asymptotically tangential to that particular value of the bulk material properties. And when you're trying to reduce the diameter, you can't go to zero over here. You will reach a certain minimum based on the technological limits. Or if you're just doing a theoretical plot, then you're trying to push the limit from a material science theoretical limit, then essentially that is the molecular dimension and or the atomic dimension. So obviously it's not going to perpetually increase, it's going to reach a particular finite maximum value. It's going to be much, much larger than the value over here, but definitely it's not going to be infinity, nor is it's going to reduce here monotonically, but it's not going to go to zero, it's going to become the corresponding bulk materials property. Now here we are discussing the ultimate tensile strength, but the same kind of logic holds for many other material properties too, in particular, let's say the Young's modulus. There are certain reasons why there are certain differences, but we'll not get into that. But overall, in a qualitative sense, how it changes is quite different. So a lot of people, when they're talking of the ultimate tensile strength, they're keeping in mind when you're talking about the fiber dimension changing, they are thinking of the force that is being taken. So many people, when you give a quick test without giving too much time for them to think, they would say yes, that ultimate tensile strength will increase, especially if you're talking of it not as a gigapascals but as pascals, sorry, newtons. So you're essentially talking about the force that it has to take. And yes, this is also true only if you take a small range, you would see a certain increase that is essentially happening over there. So monotonically increasing, it would be in some cases true if you're plotting a force, but ultimate tensile strength is not a force, it is a stress. It's the maximum stress that that material can take in a particular direction. So the other thing is those people who typically say it's a material property. Now you're saying that is, no, this is a geometric feature. So you're plotting a material property. You know UTS is a material property. You're plotting it versus a dimension, which is a geometric property. So obviously a material property should not depend on geometry. Therefore, it is a constant, which is also true when you go to a certain range. For example, when you go to rods, larger and larger rods, you may not find too much of a variation there. It will be almost a constant over there. But so when it depends on the range of your fiber diameter, some of these things may or may not hold good. Now, the third thing is, of course, a monotonic decrease. Once again, it's close to the answer, but still not right, because this should essentially go to zero. which it will not, and it could also go up in the other direction when you increase it to, let's say, the diameter you're reducing it towards 0, you have to have the strength going to infinity, which is also not the case. So, yeah, so this is something that we did in the online course that we had a couple of years back during the COVID pandemic. So people had voted, etc., and then we essentially said that from the overall discussion that we had following that, yes, this is going to decrease, but it's going to have certain limits on either side depending upon the range that the fiber diameters are going to have. So what are those limits is essentially what we tried to discuss, and as we already said in this class, in terms of this, what is the maximum it goes to. So this is, I think we did for glass over here, glass. So the data that we have here is for glass. So glass fibers and eventually getting into glass rods. So glass data, but the trends will be similar for other materials, not for essentially the same reason, but at the material level, there's a certain improvement that is happening. One is because of the orientations of the microstructure. Second is because of the reduction in the surface crack densities. One of them dominates over the other depending upon which regime you are in, but both are essentially improving as you reduce the fiber diameter. So here, let's say we're looking at from 10 to about 100 microns size in the fiber cross-sectional diameter. The apparent reason here is the lower probability of the failure-inducing surface cracks, which are generated typically during your fabrication process and could also happen during handling. Remember, these are very flimsy, these fibers. So sometimes you might have fabricated it with really superior properties. Unless and until it's handled properly, you can generate new and additional surface cracks and reduce these properties quite drastically. So you have to be very, very careful in handling these even post fabrication. And here we see that the limit as it goes, in the case of glass, it extrapolates to the cohesive strength between adjacent atomic layers, and which is about 11 GPa in the case of glass. And the fiber geometries harness a much larger increase in the ultimate tensile strength and the Young's modulus for any given material. So your typical application cases, we saw a few numbers in the previous slide as well, would not be as high as 11, it will not be as low as what you're going to have over here for the bulk material, somewhere in between. So typically of the order of 4 GPa, etc., for many glass fibers. Now, when you go to the bulk, you see the huge reduction that happens. That's why glass as a bulk may not be used in very rigorous applications where the loads are very, very large. You may not find it. You still find it in many civilian structural applications as well. For example, staircases or certain portions of buildings, etc., which are built from glass. But in many cases, those are kind of laminated glasses and some other way in which you're building strength into it. But essentially, totally bulk glass you see over here, 0.17 gigapascals is the absolute tensile strength that you have. So if tension is the main load over there, obviously it's not a great choice of material that you have over there. So yeah, I think we can go. So any questions on that till what we had over there? Okay, so just that these actual numbers will vary case to case, and also when you change, instead of your ultimate tensile strength, you're going to go for Young's modulus, and the reason also could change. What is the physics or the material science that is involved over there? But predominantly you would see this kind of qualitative behavior, and there are two reasons to it. One is closer to this, you're essentially the orientation of the material that is involved, and over this range over here, it's in terms of the reduction in the surface crack densities that you have, which is what is making a lower fiber diameter much more critical. And that's why also we talked about the fiber having superior properties compared to the particles. So the particle kind of, again, the particle depends upon how small the particle that you're essentially going into, but the fact that when you are going to use it in a composite, the orientation, etc., becomes important, and there the control over a particle's orientation much more difficult compared to the control of the overall orientations of the fibers, which is why fiber composites are much more popular in high-end applications like flight vehicle structures. Yeah.
Look at the Young's modulus when it comes to reducing the fiber diameter. Not sure about glass, but if we go into metal, will there be such a large drastic increase?
No, see, large or small, that is a quantitative thing. We are saying in a qualitative sense. In a metal, what is essentially going to happen is as you go for the smaller and smaller dimension, also depends on the specific manufacturing process involved for the smaller dimensions. But if you're doing it appropriately, you are going to essentially get that crystalline geometry aligned to a particular direction, and because of which you're going to get an increased property. Especially if you're talking of an alloy. So what is, again, how much you're going to be able to push this may not be as large. For example, in the case of carbon fibers, you're essentially moving towards a carbon nanotube. So rather graphene in a 2D sense, but then the carbon nanotube, that is a 1D structure which is formed by folding over your graphene. So that particular value quantitatively, yes, it will change. But and also how drastic it is, all those things will change. But essentially, this is what you're looking at, because in the actual usage of a composite and the choice of your fiber, you don't have this whole range that you're actually going to discuss. There's a smaller range that you're going to discuss, and within that range, the typical fibers that there are, you are going to have a drop, and you will try to push your limits to what is physically permissible, what is your technology permitting, what is your cost permitting, what is your availability from a geopolitical kind of a situation permitting. You will try to push your limit to the max because you are trying to get a superior property. But again, the cost analysis, etc., all this will come into picture. But purely from a technical point of view, you would want to try and push your diameters to be as small as possible, even in a metallic fiber. Yeah. So see, essentially what is happening is, yes, in terms of the actual failure that is going to happen, it is because of those cracks growing, and eventually the crack grows through the entire cross section and it fails. Yes, so the crack is going to have a huge impact on the ultimate tensile strength, but it's not that it will not have an impact on the Young's modulus, because let's say you're starting with very small stress. Yes, it will not fail, but the fact that you have a crack means that it will be much more flexible there. One case I don't have a crack, the other case I have a crack. Where I have a crack, this is going to be a little more flexible. So in other words, for the same stress that I'm going to apply with the crack, this is going to increase its length a little more compared to the case where the crack is not there. So essentially that is what is happening over there. So here we are not talking at the specimen level that we are usually used to, but here we are talking at a fiber level. So it's purely a material property that we are still talking about. Whereas at the specimen level, when you're having an actual crack which is visible to the naked eye, then you're essentially saying, oh, no, it's not a material property we're discussing. It's purely because of the one specimen is not manufactured properly, the other is manufactured properly. Obviously, you're going to get very different results from that. But here, at the fiber level, let's say you're talking of, let's say, a 20 micron fiber and a 10 micron fiber. You are not able to visually see those damages or cracks that are there, but the fact that one has more crack density will make it a little more flexible, and therefore its Young's modulus lesser compared to the one which is having lesser number of crack density or lesser crack density.
So the same reason we are excluding bulk cracks from crack density dimension. Defining crack density, we are considering only surface cracks.
Yes, yeah.
Not bulk.
Yes, see, because as you go for lower and lower dimensions, the interior geometry will typically be reasonably good. The problem will typically be more in terms of the surface crack densities. Because the surface crack is a function of how you're manufacturing as well as how you're handling. So it's going to make a huge difference. Whereas the interior, once you go for lower and lower dimensions, you're going to, with a reasonably established manufacturing technique, you're not going to bring in too many interior cracks. Okay, so yes, there could be some low-cost manufacturing techniques, or if the involves certain skilled labor and you're not having that, etc., there can be interior cracks also could become a huge issue. But once you go for some medium-sized fibers, yes, they are as important as your surface cracks. Your interior cracks also become important. They could be sizable, and their impact on the material properties could also be sizable. Yeah.
So you mentioned that fibers are better than the particles because there may be some challenges while orienting the particles. So, like, but the particles will be mostly spherical, or are there some other shapes which may pose these challenges?
Yeah, yeah. So the orientation is one aspect of a distribution. The other is in terms of the uniformity. So the volumetric uniformity that you're going to have. So if there are certain regions which are matrix rich, they will become the source of crack initiation, and then things can grow out of that. So that is the main reason that you have over there. And also the particle is such that its property is not superior in one particular direction compared to the other, right? So it has no anisotropy that is involved. So here you're essentially trying to take advantage of your prior knowledge in a structure that you're designing. What is the direction in which I'm getting my dominant loads? I want to make it stronger and stiffer in that direction. I don't care if it's going to be lesser strength and stiffness in the other directions. But in reality, what happens is you will have certain off-design stresses or other lower level of stresses, so you're trying to put it in the other directions. But if you're talking of, let's say, the two examples of low-cost composites that we talked about, SMC and BMC, the sheet metal compound and the bulk metal compound, there you're essentially having the fibers also in a random way. So there it would not matter too much whether you have particulate composites or fiber composites. You might end up with a reasonably good correlation. The difference will not be too much. But once you go for longer and longer fibers, the fact that you're taking advantage of that anisotropic behavior. We saw, for example, when we plotted the carbon fibers epoxy from 0 to 90, we saw a drop of about 14 times. So a factor of 14, 1,400% is what we are looking at. So there's a huge difference that is going to happen in the case of the fiber.
And will we observe a similar trend when we vary the length of the fiber? Here we have varied the diameter of the fiber. So will we observe a similar trend when we change the length?
Yeah, see, as long as we are talking of more than 10 mm, as we talked about in the case of the long fiber, you're not going to have too much of a difference once the matrix comes in. Right now, we are purely discussing only how the fiber behaves all by itself. But once the matrix comes, anything which is 10 mm or more should have a reasonable performance that you're going to have. Once you go for smaller and smaller dimensions of that fiber, you're essentially approaching from a fiber reinforcement to a particulate reinforcement, and there you would have a difference cropping up, otherwise not. Yeah, so I think we'll get into the next thing about the matrix in the next class. So this concludes with the fiber, why we are using a particular geometry of the reinforcement. Yeah. Thank you.
Particulate composites, if we are able to spread the particle uniformly, then will it be isotropic?
Yes, if it's reasonably spread out. See, there are two things. The two extremes, if you go, it's completely random. Then also in an overall bulk sense, you're going to get into isotropic. It's completely oriented in a particular way in both two different directions. You're going to get almost equal properties in both directions. It's somewhere in between that the problem of difference in different directions comes in, and also the possibility of certain regions not having the particles at all for a fairly large volume size unit cell. So then that becomes a weak link in the chain, and cracks could originate there. Because right now we're talking of very large ranges in the x-axis. typically that is not what is discussed when making a choice. There's a certain smaller domain in which you're operating, and there the number of factors which influence are much smaller. It's much more easy to make the decision. Here it's purely from a theoretical point of view, trying to understand why particular fiber geometry, so you're trying to take a much larger range in the x-axis. Okay, thank you.